Right now, in the canopy above your house, an invisible Cold War is taking place. While you sleep, work, and go about your daily life, a highly sophisticated network of operatives is conducting surveillance, stealing trade secrets, and engaging in psychological warfare. When we think of intellectual property theft, we think of cybersecurity firms, military black sites, and international espionage. We assume paranoia is a strictly human condition. We are wrong. If you look out your window and see a crow sitting on a power line, you probably think it's just resting. It isn't. It is conducting surveillance. It is mapping resources, analyzing vulnerabilities, and watching its neighbors. Within the scientific community, behavioral ecologists have uncovered a shadow economy operating in our own backyards, an economy built entirely on biological espionage. By the end of this video, you'll know exactly how this system works, why it is far more advanced than most people realize, and what it reveals about the nature of intelligence itself. Today, we are going to reverse engineer the terrifyingly advanced intelligence of Corvids. We will investigate the black sites where they hide their technology, the active countermeasures they deploy, and the chilling realization that they know exactly when you are watching them. Welcome to the Paranoia Protocol. To understand why a bird would need counter-surveillance, you first have to understand their economy. In the Corvid world, calories are currency. And just like in Silicon Valley, there are two ways to get rich. You can invent something revolutionary, or you can steal it. On the islands of New Caledonia, crows don't just use twigs. They are biological engineers. They manufacture complex standardized tools, like the stepped-cut pandanus hook. This isn't just a stick. It is a biological patent. The New Caledonian crow, studied extensively by Dr. Gavin Hunt from the University of Auckland, does something no other bird on the planet does with the same degree of precision. It cuts leaves from the pandanus plant at a specific angle, creating a serrated, hooked probe that can reach into deep crevices and extract grubs. The geometry of this tool is not random. It is standardized across populations. Different groups of crows in different parts of New Caledonia produce tools with slightly different shapes, but each group is internally consistent. These are not accidents. These are manufacturing traditions. Now consider what it costs to produce this technology. A young crow does not hatch knowing how to make a pandanus hook. Research published in the journal Science in 2002 documented this manufacturing process, and what it revealed was staggering. A juvenile crow spends months, sometimes over a year, watching adult crows work before it can reliably produce a functional tool. The motor learning required is extensive. The crow must learn the correct angle of the cut, the length of the hook, and the tension needed to keep the leaf from snapping. Every failed prototype is a caloric loss. Every botched cut is wasted energy. The crow has essentially invested the equivalent of a 4-year engineering degree into a single piece of equipment. And that tool, once perfected, dramatically increases the crow's ability to extract food from locations no beak can reach. Studies observing New Caledonian crows in the field found that tool-using birds extract food from deep crevices at a rate that significantly outpaces non-tool users in the same environment. The tool is not a luxury. It is the difference between survival and starvation. This is where the economy gets brutal. Behavioral ecologists use the word kleptoparasitism to describe what happens next. It means, in plain language, theft. One animal steals food or resources directly from another. In corvid populations, kleptoparasitism is not an occasional crime. It is a full-time profession for certain individuals. Researchers observing crow and raven populations in the field have documented birds that dedicate significant portions of their day not to finding food themselves, but to watching other birds find food and then taking it. Think about what this means for the inventor crow. It has spent months learning tool geometry. It has burned through its own caloric reserves in the learning process. It has finally produced a functional hook. And now, the moment it extracts a grub from a deep crevice and sets the tool down for a single second, a spy crow that has been watching from 30 meters away swoops in and takes both the grub and the tool. The spy crow didn't spend a year learning to make that hook. It spent 30 seconds watching where the inventor put it down. The return on investment for theft is astronomically higher than the return on investment for invention, at least in the short term. This is not a metaphor. This is the actual economic calculation happening inside the Corvid social structure every single day. An estimated 80% of crows in certain studies have been observed using tools to obtain food, according to research published in Science in 2002. This means tool use is widespread enough that the knowledge has propagated across the population. But it also means that the population of potential thieves is enormous. If most crows understand what a tool is and what it does, then most crows understand the value of stealing one. Because there is no patent law in the canopy, an inventor has exactly 3 seconds before a spy steals their prototype, reverse engineers the geometry, and bankrupts them. This constant threat of theft has forced crows to evolve a terrifying psychological defense mechanism. If you are constantly at risk of being robbed, you develop paranoia. But for a crow, paranoia isn't an emotion. It is a highly calibrated biological protocol. They live their entire lives inside a biological panopticon, a state where they must assume they are always being watched. The panopticon was originally a prison design concept, where a single guard could observe all inmates without them knowing when they were being watched. The result was that inmates had to behave as if they were being watched at all times, because they could never be certain they weren't. Crows live in this condition permanently. Their environment is the prison. Every branch, every neighboring rooftop, every gap in the canopy is a potential observation point for a rival. Before an inventor crow even begins to manufacture a tool or hide a cache of food, they execute a perimeter sweep. This sweep is built on a biological capability that should make you genuinely uncomfortable. Crows have what researchers describe as lateral-eyed vision, meaning their eyes are positioned on the sides of their heads rather than facing forward like human eyes. This gives them a visual field approaching 360 degrees. But the critical detail is not the width of the field. It is the precision within it. Research into avian gaze detection has shown that crows do not simply scan for the presence of other birds. They track the specific direction of a rival's gaze. A crow can calculate, based on the angle of another bird's head and the positioning of its pupil, exactly what that rival bird is looking at. This is not guesswork. Studies on corvids and other birds have demonstrated that they respond differently to a rival whose gaze is directed at them versus a rival whose gaze is directed away. They are reading eye angles the way a poker player reads tells. This gaze tracking creates a sophisticated layer of information warfare in the canopy. The inventor crow, before it begins any sensitive operation, will scan the surrounding area and attempt to determine not just whether rivals are present, but whether any of those rivals are actively looking at it. If the inventor detects that a spy crow's gaze is oriented in its direction, it will not begin work. It will wait. It will feed casually on something unimportant. It will perform what researchers have described as a displacement activity, an action designed to communicate to the spy that nothing interesting is happening here. The spy, of course, knows this tactic exists, and so begins one of the most sophisticated psychological exchanges in the animal kingdom. The spy crow has its own countermeasure. If it is too obviously watching the inventor will not proceed. So the spy employs what can only be described as a deliberate misdirection of its own gaze. It turns its head away. It appears to be feeding on the ground below it, but it is using its extraordinary lateral vision to continue monitoring the inventor from its peripheral field. The spy is watching without appearing to watch. The inventor, aware that a spy might do exactly this, has to make a judgment call. Has the rival genuinely lost interest, or is it performing a false disengagement? This is not instinct in the simple sense. This requires modeling what is happening inside another bird's mind. It requires understanding that another creature can have intentions that differ from their outward behavior. It requires, in other words, a theory of mind. The back and forth between inventor and spy is a real-time chess match, played in silence across a gap of 30 or 40 meters. Each bird is running a continuous internal simulation of what the other bird knows, what the other bird wants, and what the other bird is likely to do next. The crow with the more accurate model of its rival's mental state wins. The crow with the less accurate model loses its tools, its food, and its caloric investment in one swoop. The spies are relentless. The look-away tactic isn't enough anymore. And so, it forced the innovators to take their operations completely off the grid. When military contractors like Lockheed Martin want to build a stealth bomber, they don't build it in a glass window factory. They build it in a black site, a highly classified, visually obscured, acoustically deadened facility. Crows have independently evolved the exact same architectural principle. Observational research on Corvid caching and tool use behavior has documented a pattern that is, once you see it, impossible to unsee. When a crow intends to perform a sensitive operation, whether that is manufacturing a tool, extracting a particularly valuable food item, or hiding a cache, it does not do this in the open. It actively selects its operating location based on the same criteria a military engineer would use when designing a secure facility. The first criterion is visual occlusion. The crow moves to the deepest available shadow in the tree canopy, positioning itself so that the dense overlap of leaves and branches creates a broken line of sight from multiple angles. A rival attempting to observe from above cannot get a clean view. A rival watching from the side is blocked by a wall of foliage. The crow has selected its position not for comfort or convenience, but for its specific geometric properties relative to the positions of potential observers. It is, in practical engineering language, choosing a location with the lowest observation probability from all surrounding vectors. This is not random. Researchers studying corvid behavior have noted that crows will bypass more convenient or more comfortable perches in favor of darker, more enclosed positions when they are about to engage in behavior they appear to want concealed. The selection is deliberate. The second criterion is acoustic control, and this is where corvid intelligence crosses into territory that should genuinely unsettle you. Tool manufacturing is not a silent activity. Tearing a pandanus leaf creates a specific, distinctive sound. Snapping a twig generates a sharp crack that carries through still forest air. Any sound produced during the manufacturing process is a signal that can be detected and interpreted by a rival. Sound travels around obstacles that block light. A spy crow that cannot see the inventor can still hear it working. Crows appear to know this. Behavioral observations have recorded crows pressing their bodies and their working tools against the trunks of large trees while performing sensitive operations. The tree trunk acts as an acoustic baffle. The mass and density of the wood absorbs and deflects vibrations that would otherwise radiate outward through the air. The crack of a snapping twig, when it occurs in direct contact with a large wooden mass, is partially absorbed into that mass rather than propagating as an airborne sound wave. The crow is using the tree as a soundproofing wall. This is not a learned behavior in the sense that a crow trainer showed it this trick. This is a behavior that has emerged from the crow's understanding of its own vulnerability. It knows that sound betrays its position. It knows that the tree absorbs sound. And it knows that placing its operation in contact with the tree reduces its acoustic signature. This is applied physics, running as a behavioral subroutine inside a bird brain. These two adaptations together, positional stealth and acoustic suppression, constitute what functions as a field-engineered black site. The crow has assessed its threat environment, identified the specific sensory channels through which it can be detected, and taken active steps to reduce its signature across both of those channels simultaneously. But what happens when the black site is compromised? What happens when a spy is right behind you and you can't break their line of sight? That is when the crows deploy their masterstroke. If hiding doesn't work, the crows deploy a psychological weapon called theory of mind. It is the cognitive realization that other beings have unique intentions. The crow thinks, I know that you know what I am doing, and I know you want to steal it. And because they possess this, they build decoy vaults. Watch the sequence unfold. A crow has a high-value food item, a piece of meat, a large grub, something that represents a serious caloric investment. It needs to cache this item for later retrieval. It knows, because it has been tracking gaze angles and running its social model of the surrounding birds, that it is being watched by at least one rival. Hiding the real item right now, in plain sight of the spy, is not an option. The spy will simply wait for the inventor to leave and then raid the cache. So the crow picks up a small stone, or a worthless scrap of bark, or a piece of garbage. It carries this object to a visible, open location, and then it performs. It digs a small depression in the soil with its beak, It places the worthless object in the depression. It covers the depression with dirt and debris, using the same careful, deliberate motions it would use if it were caching something genuinely valuable. It even performs the post-caching behavior, tamping the soil, rearranging the covering material, stepping back, and appearing to assess the cache site. The entire theatrical production looks, from the spy's perspective, indistinguishable from a real caching event. This is a lie. A constructed, intentional physical lie. The Crow has built a fake vault, and it has done so specifically because it has modeled the spy's likely future behavior. It knows the spy wants to steal. It knows the spy will go to the cache site after the inventor leaves. It has calculated that feeding the spy false information now will cause the spy to waste its time and energy excavating a worthless hole, while the real item, the actual food, has been hidden elsewhere. In some documented observations, the real item is held in the Crow's throat pouch during the entire false caching performance, concealed inside the Crow's own body, while the decoy operation plays out in front of the spy. Consider the computational load this requires. To execute a false cache, the Crow must first hold in its mind a model of what the spy currently believes. It must understand that the spy believes the inventor is about to hide something valuable. It must then construct an action sequence that reinforces this false belief. It must maintain the performance convincingly enough that the spy does not detect the deception. And it must simultaneously retain the location of the actual item and execute a genuine cache somewhere the spy is not watching. This requires the Crow to run at least two parallel mental models simultaneously. Its own knowledge state, including what it knows the item actually is, and where it will actually be hidden. And the spy's knowledge state, specifically what the spy believes, based on what the spy has been allowed to observe. The Crow is manipulating a mental model of another individual's beliefs to produce a desired real-world outcome. Research into corvid behavior, including studies on western scrub jays, which are close relatives of crows within the Corvidae family, has documented precisely this false caching behavior. And critically, the behavior appears only in birds that have themselves previously stolen from others. Crows that have experience as thieves are more likely to deploy deception when caching. They know how a thief thinks because they have been thieves. They are using insider knowledge to construct better counterintelligence. The false caching behavior has also been documented, shifting dynamically in response to the spy's position. If the spy moves, the inventor Crow adjusts its deception accordingly. If the spy gets a cleaner line of sight on one side, the inventor shifts its body to obstruct it. This is not a fixed behavioral script playing out in sequence. This is live, responsive, real-time tactical deception. Now place this inside the broader social structure of the corvid world. Crows are not solitary animals. The American crow, Corvus brachyrhynchus, lives in complex social groups. The global population of American crows is estimated between 31 million and 42 million, according to the North American Breeding Bird Survey. These birds interact constantly, in roosting groups that can number in the thousands, in family units that maintain long-term relationships, and in territorial disputes that can persist for years. Within these social structures, information about who is a reliable ally, who is a thief, and who poses a physical threat is extraordinarily valuable. And crows do not just use this information themselves. They share it. Over 20 distinct calls have been identified in crow vocalizations by researchers studying their communication systems, each potentially carrying different information about the nature and location of a threat. A 2020 study highlighted that crows may use different calls for different predator types, suggesting they are communicating not just that danger exists, but specific details about what kind of danger it is and how to respond. This is not a single alarm call that means danger is near. This is a call system specific enough to encode behavioral instructions. Dr. John Marsluff from the University of Washington, one of the leading researchers in crow cognition, has stated directly, "Crows are incredibly intelligent, but what is truly fascinating is their social learning. They can teach each other about threats, which is a crucial survival skill. Social learning in crows operates through direct observation, through vocal communication, and through what researchers describe as mob behavior around perceived threats. Crows have been observed gathering around deceased crows in what some researchers describe as crow funerals. These gatherings, documented by Marsluff's team, appear to serve a learning function. Crows that witness the gathering near a dead crow become more cautious around the location where the death occurred and around any associated stimuli, including humans who were present nearby. This is how threat data propagates through the network. An individual encounter with a dangerous predator or a dangerous human does not stay with the individual. It enters the social information system of the group. Other birds observe the response, hear the calls, and update their own behavioral models accordingly. And this brings us to a capability that was formally documented in a University of Washington study published in 2008. Crows can recognize and remember individual human faces for over 5 years. This is not general wariness around humans. This is targeted, persistent, individual identification. In the Seattle research conducted by Marsluff and his team, researchers wore specific masks while capturing and banding crows. Afterward, crows that had been captured responded aggressively, specifically to humans wearing those masks, scolding them, dive-bombing them, and rallying other crows to join the harassment. Crows that had not been captured, but had observed the response of captured birds, also learned to respond to the masked faces. The threat data had transferred through the social network to birds that had no direct experience of the original threat. This facial recognition capability runs through the same cognitive architecture that powers everything else we have examined. The gaze tracking, the theory of mind, the false caching, the acoustic black sites. It is all running on the same biological hardware. A brain that, despite being housed inside an animal we have spent centuries dismissing as a simple scavenger, performs computations that most creatures on this planet cannot come close to matching. The Corvidae family includes not just crows, but ravens, magpies, and jays. Researchers at the University of Washington and the University of Auckland have collectively built a body of evidence over the past 2 decades, showing that these animals plan for future events. A 2015 study highlighted this capacity in corvids specifically, suggesting advanced cognitive functions similar to those found in primates. They recognize themselves in mirrors, a test that most animals fail. They use tools, modify tools, and manufacture tools. They deceive. They model the minds of rivals. And they transmit knowledge socially across generations. The debate within the research community centers on a specific question. Are these behaviors genuinely driven by something like conscious planning and foresight? Or are they complex, but ultimately reflexive responses shaped by evolutionary pressure? Some researchers argue that the evidence for planning and deliberate deception is strong enough that the distinction becomes difficult to maintain. Others argue that attributing conscious thought to a bird oversteps what the behavioral evidence can actually prove. What is not debated is the behavioral output. Regardless of the internal experience driving it, a crow performing a false cache in response to an observed spy is producing a behavioral sequence that requires modeling another individual's beliefs, constructing a deceptive physical display, and managing the real object simultaneously. The output is identical to what we would call strategic deception if a human did it. And the crow does it alone, in a tree, without a committee, without a briefing document, and without a salary. Consider what this means for how we understand intelligence. We tend to think of cognitive sophistication as something that scales with brain size, or with evolutionary proximity to humans. Crows challenge that assumption directly. Their brains are structured differently from mammalian brains. The region in the corvid brain that appears to support higher cognitive function is the nidopallium, a structure that functions as the avian equivalent of the prefrontal cortex, the region in human brains associated with planning, decision-making, and social cognition. The nidopallium does not look like a human prefrontal cortex. It is organized differently, structured differently, and evolved independently along a completely separate line from mammalian neural architecture. Intelligence, in other words, did not evolve once. It evolved at least twice, possibly more. And in crows, it evolved to solve exactly the same problems that drove the development of human cognitive complexity: social competition, resource management, deception, and counter-deception. The arms race between inventor crows and spy crows, the black site construction, the acoustic camouflage, the false caching, the gaze tracking, the social transmission of threat intelligence. None of this was designed. None of it was programmed. It emerged from the relentless pressure of an economy where cognitive advantage translates directly into calories, and calories translate directly into survival and reproduction. Every crow alive today is the descendant of birds that won this arms race in their generation. Every behavior we have examined is the behavioral inheritance of millions of years of selection pressure that punished cognitive shortcuts and rewarded increasingly sophisticated models of the social world. When you look at a crow sitting on a power line, you are looking at the current champion of an evolutionary tournament that has been running longer than our species has existed. The decoy protocol proves that Corvids understand deception on a level we previously thought was exclusively human. But hiding your tools is completely useless if the thief already knows exactly who you are. What happens when a spy crow realizes it has been tricked? It escalates. They don't just remember where you hid your tools. They map your face. And they upload your facial data to a decentralized, generational biological database. They don't just remember you. They dox you. To see exactly how this terrifying biological facial recognition network operates and how it targets humans, you need to understand the Seattle caveman experiments. Click the video on your screen right now to step into the network. Do not look away. The spies are already watching. I'll see you in there.